Okay, so since I didn't have enough time to cover everything I wanted to on Monday, I wanted to just follow up um, with a bit of a suffix related to address spaces to give you guys a little more detail. And I think this will at least give you something to mull on during the polar blast that we're currently experiencing. And then we'll re-continue with the regular lectures next Monday. Okay, so on to more virtual memory stuff. So we talked about address spaces in a pretty high level way. I wanted to dive into that a little more and talk about the regions that comprise an address space. Okay. So the address space itself is pretty uninteresting, right? So we did a little bit of talking about what an address space actually is, right? And that's just like a set of numbers, essentially, right? But what's really interesting about these address spaces is their regions, okay? The subsets of the address space to which we attach some specific meaning, okay? So, for example, right, this is our usual process address space that we're used to, right? So we have the kernel, we have the stack, we have the heap, data and code. Nothing new here, right? But what's interesting is the bytes that are mapped to by these regions. Okay, so at least for this class in operating systems, these regions, right, these sets of numbers, they map to some physical thing, and that physical thing turns out to be some bytes in RAM. Okay, now it always doesn't have to be RAM. It could be something else. But for our purposes now, we'll consider DRAM. Okay. So when we look back at that usual user process address space, right, there is a particular set of addresses, right, these stack addresses, and we attach some meaning to those, which means they will map to bytes in memory, which correspond to the stack. Okay, and the operating system will ensure that those bytes are used for stack space, will be used for local variables and locally scoped things. Okay, but it doesn't have to be this way, right? So process address spaces, you can construct them yourself if you want, right? And the operating system can kind of choose what these different regions mean, and they can mean a lot of different things. There are some pretty clever hacks out there which will actually overwrite portions of your address space. Yes, you can construct your own address space as a user process, right? So this is often used if you want to inject some code into a running process. You can actually map a new region, which will then correspond to bytes which hold some evil code, like I have here on the slide. Okay. Now you can actually see on Linux, you can actually see the map that has been constructed for you by the kernel. Okay, so here I run this command cat/proc/self/maps. Now if you haven't seen proc before, this is a very special file system that Linux exports, and it's basically like an informational file system. So each file inside of this file system has some interesting data that the kernel is keeping track of, and you can get it out just by reading it, right? So you can cat proc/self/maps, and you know how to implement cat now, so you can imagine what this is doing under the covers. Okay. Now, what does maps mean? That's pretty obvious. This is the address space, right? This is the mapping from addresses to bytes that the kernel is giving this particular process. And there are many such files. Okay, so it turns out that there are one of these files for each process in the system. Okay, so self turns out to be a shorthand. Right? This is a shorthand for my process. Okay, so this is going to correspond to, this is going to turn into the PID for cat, right? So I can actually provide an arbitrary PID in here as well. I can actually show you that on the terminal. I can pull this up. I'm logged in here to one of our lab machines, and I can see I have some processes running here. Let's just grab one that's going to stick around. So this GNOME shell, right? So that's PID, let's just say 22547. So I can say cat slash proc slash 22547 slash maps, and there's another address space. If I want to actually be able to page through it, I can say less instead of cat, like so, and we can see that this is a pretty complicated address space. Okay. Now if I go back to the slide here, I've highlighted some interesting parts of this, in this case, cat's address space. Okay, so we have the code, right? We have the heap, which we're used to. I'll skip this. We have the stack and some source of kernel's cleverness. You can ignore that for now. These are regions that the kernel has said map to special bytes in the address space. Okay, so these bytes right here, these code bytes, these map to the program binary, which is sitting somewhere on disk or is loaded into memory. Right? These bytes at address 5563, whatever, those map to the heap. Right? These things are libraries which your program depends on. Okay, so the kernel will actually, the loader, which is part of the kernel, will load libraries into the address space of the process and will make them correspond to bytes in memory. So they don't necessarily map bytes to these address spaces. Okay, so if we consider a different type of address space, right? Before what we were seeing, this is a virtual address space. Okay, what we see here is a physical address space. Okay, so these are physical addresses, and they are going to map to some entity in the physical world. Okay, in many cases, they map to RAM, right? They map to, in this case it says, depends on system RAM. This will map to RAM. Okay, but other things do not, right? So address A0000, right? It has some meaning, which turns out to mean this byte will map to your GPU, right? This will map to the thing that generates the display in front of you. These bytes right here, these don't go to RAM. They go to some other chip on your motherboard which holds the BIOS. Okay, and you'll learn a little bit more about the BIOS in your next project. Okay. Now this particular address space is the PC 32-bit physical address space, and it kind of depends on which motherboard you have, and also depends on the system, right? So like if I have a Mac machine, it'll look entirely different from this. Okay. You can also get this map, right? So what I'm doing here, and for this command you have to have root access on your machine. So if you have a virtual machine, you should be able to do this, but you have to say sudo cat /proc/iomem. And this is going to tell you where the kernel has mapped things in the physical address space to different devices and different things that are connected to the system. Okay, and I've highlighted some of the things that I can recognize here, right? So here's our BIOS. It's mapped at F0000. This system RAM region, this actually goes to your DRAM chips, right? It goes to the DIMMs plugged into your motherboard. This region right here, this is where the kernel lives, right? The kernel's code and data. And we have some other things here too, like a PCI bridge, fancy PCI device, right? It's got different things under it. We'll see later on in the course what these actually mean. So don't worry about them for now. Let me just actually show you that live. So I can just say sudo cat /proc/iomem. This guy asks for a password. Right, let's do that with less. Okay, so there's a lot of stuff in here, right? So the dump that I had on the slide was a little simpler because that was actually in a virtual machine. But the server I'm logged into right now has tons of interesting devices attached to it. So there's a lot of output here. Okay, and it's not worth going through that right now. Okay, so how does this all work, right? So especially this physical address space. I told you that these different address regions somehow correspond to different devices and different bytes of memory in the system. it's interesting to find out how that works. I didn't have time to cover this in class, but I'll spend a little more time on it here. So your system is not just your CPU, right? And I think I've mentioned this before in class. It's kind of like a little distributed system with components connected to each other, right? And all these components are sitting on your motherboard. So this is kind of an old depiction. Things are more or less conceptually similar nowadays, but the details differ. But essentially what we have here is a CPU, right, your processor, and hanging off that CPU is a bus, right, just a set of wires. We typically call that the system bus. That system bus is going to connect to another chip that we call the memory controller, right? In the old days that was called the North Bridge. And this thing, its job is to route addresses. Okay. Its job is to determine what the addresses mean. The addresses coming off of the CPU. All right. And notice in this system we also have our DIMM chips. This is our RAM. We have a PCI bus, which is going to connect us to all the devices in the system. Right? And since we have multiple devices, we have to be able to send commands and data back and forth and figure out where those commands and data go to. Right? And that's what this PCI switch is for. Again, we'll talk about PCI more later on. So say I have on my CPU, right, I have some instruction which says mov some data at this address, this physical address, and put it in a register. In this case I'm saying put it in register EAX. Okay. So that means that this address that I have here, this physical address, is going to go out the back end of the CPU on the front side bus, and the memory controller is going to see that address and it's going to say, you know what, this is RAM. Right, this is actually DRAM, and I need to route that over to my DIMM chips right here. Right, so it'll send that address along. The DRAM chips will respond with data, and that will go back over via the memory controller to the CPU. Okay. Now, if I put some other address, okay, it doesn't necessarily turn out the same way. So here I'm saying move the character A to address B00000. Now this turns out to be a very special address. This is an address of the frame buffer, which holds the pixels for your display. And that frame buffer is living on some piece of memory in your GPU. Okay, the GPU is going to draw those pixels on the screen. So then the question is, how does this get routed over here to this GPU? So this time things go a little differently. I put the address B0000 out on my pins of the CPU. Then gets routed along the system bus to the memory controller, just like before. But now, the memory controller sees that this is a memory mapped device, right? And in particular, it's a PCI device. So what it does is it sends out a packet, right? It sends out a packet on the PCI bus. And bus is a little bit of a misnomer here. It's actually not a bus anymore these days. It's a little interconnect, which is why we're sending packets. But the memory controller constructs a little packet, and it stamps on an ID to it. In this case, it's saying ID 0, which corresponds to the GPU here. If it meant the network interface, it would have put ID 1, but it did not. And then it has a payload, right? In this case, our payload is the character A. Okay. So that packet then gets routed along this little PCI network over to the GPU. And the GPU will then draw the pixels on your screen, and we'll be able to see the character A show up. Okay, so this is kind of the nuts and bolts of memory mapped devices and how the memory controller decides where different loads and stores go to in the system. Now, on these days, right, this memory controller here is actually kind of sucked onto the die of the CPU. So this translation happens before the address even goes off the CPU's address pins. Right? This makes things a little more efficient. It's especially important if you have a very high throughput GPU, like a NVIDIA V100 or something like that. Okay. So that's basically all I wanted to talk about today. Just kind of dive in a little more detail of how things are working under the covers with physical address spaces.